Dear learners, greetings from IIT Guwahati. We are in the Applied Thermodynamics course, Module 5, Refrigeration and Air Conditioning. Till last class, we covered 3 lectures which are based on vapor compression refrigeration system and vapor absorption refrigeration systems. In addition to that, we discussed about refrigerants and their nomenclature as well as designations. Now, we will move on to air conditioning processes, its thermodynamic aspects. So, under this heading we have 3 lectures. Lecture number 4, Fundamentals of Psychrometrics, then 5, Air conditioning processes, 6, Cooling tower and air washers. Now, we are in the lecture number 4, that is Fundamentals of Psychrometrics. Under this lecture, we will be addressing the following topics: what are the psychrometric principles, why you are going to study psychrometrics, and different properties of moist air. So, till this point of time, when you talk about air, we only talk about dry air, but whenever you are dealing with psychrometric, then you must deal with moist air, and we have to evaluate its properties to address all the thermodynamic fundamentals. Then we will move on to psychrometric charts. So, on this psychrometric chart, we are going to say that how you are going to calculate or evaluate the properties of moist air on a single psychrometric chart. So, this is the topics that we are going to address in this lecture. So, let us start the first one, that is psychrometric principles. So, the very basic fundamental aspect is that why we should know the psychrometrics, what is the requirement. Now, when you dealt with refrigerations, our main attention was focused on coolness in terms of temperature below 0 degree centigrades or in that range. Maybe we also require comfort cooling, as well as some situation we require the temperature to be -10, -20 degree centigrades. So, that depends on the cooling requirement. However, in some situations, in addition to the temperatures, we also have to look into the water vapors present in the air. So, while looking into water vapor present in the air, we have to find its or you have to quantify its value, and for which some of the properties we are going to determine. So, when you talk about air conditioning processes, it is essentially simultaneous control of temperatures which is relatively low. At the same time, we also have to look into the water vapors quantifications present in the air, so as to have comfort cooling. So, these two simultaneous control is possible only when we know the moist air and its properties. So, for that study, those studies that involves the dry air as well as water vapors present is known as the psychrometrics, or many times we call as a hygrometry. In this this particular figure shows a kind of applications where the air is intentionally made moist. So, one way, when you increase the water vapors in the dry air, such a process we can call it as a humidifications, and in some cases we can also think of removing air from the water vapor. So, you can say it is a dehumidification process. So, in one sense we have given here where air is allowed to pass through a chilled water circulating coil. So, as a result, the air gets humidified as well as temperature also comes down. So, it is a cooling and humidification. Another way is that when you are using water eliminators, so you have to remove the water vapors present in the air. So, that way we can say is a when we are taking it out, we can say dehumidification of air. So, there are many processes: heating, humidifications, cooling, dehumidifications. Many combinations are possible depending on the requirement, and such a study requires the knowledge of humidity as well as the temperatures. And for that thing we have to define what is a moist air. So, basically moist air in a layman says we understand when there is some water vapors present in the air. So, we say it is a air is moist. So, for example, thermodynamically if you take a control volume or certain volume, and in that volume we have a mixture that contains dry air and water vapor, and these mixtures are stored in this container, and from which we can measure its temperature T and pressure P. So, what we say it is the mixture temperatures irrespective of air or water vapor, the mixture temperature is at T, the total pressure that is measured is P. But however, within this moist air, depending on the quantity of water vapors, the total pressure remains same, but the component of pressures in the form of dry air or water vapor may be different. And of course, even though they are at same mixture temperatures. So, that is the reason we have to quantify how much water vapor is present, what is the water vapor pressure inside this moist air. Such a study, to know the study, you have to know this moist air. So, one way to look at this problem is that in a sense that when you talk about water vapors, so in a and water is treated as a pure substance. So, we can say whenever we are in the saturated vapor region and beyond that saturated vapor region, when you deal with a mixture, then we can say we can use our steam table data to quantify the correct state or the magnitude of water vapor corresponding to that temperatures. And of course, since it is a vapor, we can also use this ideal equation of state for water vapors, in which we can say that m is the molecular weight of the mixture. Now, when you say molecular weight of the mixture, we have to say dry air as well as the water vapors. So, you can use that equation of state to quantify or find out the mixture pressure. Another important aspect in the psychometric principle, you have to recall this Dalton's law. In general, the Dalton's law says that if you have in a gas mixture, if there are n number of gases and they are kept in a container for which the total pressure is P and the temperature is T, that means the entire mixture is at a temperature T, and each gas has certain number of moles. So, gas 1 has N1 number of moles, gas 2 has N2 number of moles. So, each gas will have its components or its contribution in terms of the total pressure. So, and we call this as a partial pressures, and for gas 1, gas 2 and so on. So, likewise we have the total pressure is equal to sum of the partial pressures of each gas. So, likewise we can say P is equal to P1 plus P2 plus Pj plus even Pn. So, that is the basic principle what we call is as a Dalton's law, and this Dalton's law we can apply to our systems, and in our systems there are only two constituents, one is dry air, other is the water vapors. So, we can say the total pressure may be equal to the partial pressure of air plus partial pressure of vapors, and this partial pressure of air we can express in the form of mole fraction Y A into P, that means Y A is the component of number of moles of mixture for the air and Y B is the number of moles for vapor. So, that way we can quantify this P A and P V, and ultimately when you put this ideal gas equation of state for air and water, we can write these equations Pa is the partial pressure for air is equal to m times R divided by Ma into T divided by B. B is your total volume, T is the mixture temperature. Similarly, we also can find out the partial pressure of water vapor knowing the molecular mass of vapor, and of course, these Pa and Pb are evaluated at same mixture temperature T. So, this is how the Dalton's law is going to be applied for our study dealing with the psychrometrics. Then moving into next principle, what we call as a saturated air. Now, when you talk about moist air, air is a moist, that means water vapor is present in it. So, for such a systems, that means if you take water as a pure substance and recall our temperature volume diagram, in that temperature volume diagram we can draw this constant pressure lines in this manner. So, one such line is PV, that is partial pressure of, that is vapor pressure PV. So, that means one value of, that means if you have a state of moist air at this point A, then at this point A we can you can draw a vertical on the temperature axis, we can find the mixture temperature. Now, that mixture temperature, the air is exist, and that state we say it is a state of water vapor present in the moist air. There are two ways in which we can bring this point to a saturation curve. So, one way is that we can cool this or compress this to reach this saturation curve at same vapor pressure. Other is we can go along the same mixture temperature and it got the saturation vapor pressure. So, the point is B, another point we can record as C. So, from A to C we can reach if you can cool this and side by side you can compress this, then we can reach the saturation curve C, and that point we say it is a saturated, but this saturated is at same vapor pressure. Other way it can reach is the saturated air state at point B, but when we are going at same mixture temperatures. So, very basic definition that we call this as a, if the mixture of dry air and saturated vapor. So, the saturated air is nothing but the mixture of a dry air and saturated water vapor. So, when the partial pressure of water vapor corresponds to saturation temperature Pg at mixture temperature T, then it is air is to be saturated. So, basically we have to, when we have to reach the saturated air, then we must recall two things. We have to go along the same mixture temperature wherever it cuts the saturation curve, and in this case it is point B. In that case we call this as a saturated air. So, any typical state of partial vapor of water vapor Pv in the moist air, the mixture temperature can be defined, but the saturated air of the mixture Pa and saturated vapor Pv now becomes Pg. So, originally when here we say the water vapor present in this mixture has partial pressure Pv, but when we are reaching the saturated state, so we say now Pv becomes Pg because pressure is increased. And of course, the amount of water vapor present in the air can vary from 0 to 1. When it is 0 it is dry air, and when it is a maximum it is saturated air. So, depending on the pressure and temperature when the mixture is saturated. Another important aspect is that when you deal with moist air in equilibrium with water. So, many times in our study of air conditioning processes, we used to be dealing with water and air simultaneously. When you sometimes the water may be in the saturated state, maybe it is maybe in a steam or it may be a liquid. So, depending on this case, the moist air can be equilibrium with water. There are many systems of interest in which we require that the mixture is in contact with liquid phase or solid phase of water. In some cases it is contact with ice also. So, we can take a situation that when you can have a systems which has a vessel containing a liquid water and above which there is a mixture of water vapor and dry air. So, if there is no interaction with surroundings allowed, these liquids will evaporate and eventually the gas phase becomes saturated and system attains equilibrium. So, this particular experiment can be done, that means we in a closed container, if we can put some liquid water with half filled, then we can and if you keep it holding, and you can find at some time, after some time we can have two distinct phases. One is complete liquid water stage, other can be in a gas phase, and in the gas phase we may have the water which is in the remaining part of this volume becomes a composition of gas, which means it is a mixture of dry air and water vapor. So, such a things we can say the mixture is in equilibrium. So, such a system can be best described accurately with certain idealization, that is dry air and water vapor, they behave as two independent ideal gas. So, one thing we can say is that for this liquid water separate treatment can be done as far as the stream table is concerned, and they are saturated liquid state. And other things we can do it, that this gas phase we can separate one part as dry air, other part can be water vapors. So, the equilibrium between liquid phase and water vapor is not significantly distributed by the presence of air. The partial pressure of water vapor is equal to saturation pressure of water corresponding to the mixture temperatures. So, these things we can make some assumption, so that we can model this moist air when it is equilibrium with water. Next thing we will move into psychrometric properties. The first properties that we are going to discuss is the humidity ratio. So, if you recall our analysis, that we have a moist air composing having certain compositions, Na is and Ma is the number of moles and mass of the dry air, Nb and Mb as number of moles of water vapor and mass of water vapors, N and M are the moles of mixture and mass of the mixture. They are kept in a container. Now, how we are going to quantify? The first way of quantifications, now when you say quantifying, then we have to define its properties. There are two ways in which this moist air sample can be described. First one, by expressing in terms of moles of dry airs and water vapor present in it. So, we call this as a mole fraction. That means, in the mixture how many moles we can define. Other way is that we can express them by their mass, in terms of their mass. So, we call as a mass fractions. There are two ways, mole fraction or mass fractions. Now, when we say humidity ratio as one of the properties, it is the composition indicated by the ratio of mass of water vapor. That means, when we are expressing in terms of mass, so we say mass of water vapor to the mass of dry air. So, that means mv by ma ratio becomes the term what we call as a humidity ratio. And if you look at this expression, omega is the symbol that is assigned for humidity ratio, that is equal to mv by ma. Now, here this mass we can express from the ideal gas equation of state for water vapors. So, in terms of molecular weight, partial pressure of vapors, and of course, we have universal gas constant, and all these things are addressed because the total volume is fixed and mixture temperature is fixed. And this similarly, we also can find out the mass of air. After simplifications, we are in the position that this equation gets simplified. We got a ratio of molecular masses for water vapor and air. So, we put their absolute values of vapor molecular masses, then we have PV and PA. So, PV, that means total pressure, if you say total pressure P and PA is your air pressure. So, we can express in the PA air pressure will be using the Dalton's law, we can write PA as equal to P minus PV, and ultimately the omega, which is humidity ratio, is expressed by simple expressions, that is 0.622 PV divided by P minus PV. So, here the 0.622 terms arises because we have taken the molecular mass of water vapor and air ratio. So, this is how one way that we represent this in terms of humidity ratio. The other way of expressing this properties is in terms of relative humidity. So, in that case what we have to use, we have to take the ratio of mole fraction of water vapor in a given moist air sample to the mole fraction of saturated moist air sample in the same mixture pressure and temperatures. So, relative humidity is defined in that manner. So, if you say relative humidity phi, so it is a mole fraction for water vapor divided by mole fraction if the air is saturated and we are evaluating at mixture temperature T and P. So, phi is equal to Pv by Ps, T and P, and here the mole fraction we can write in terms of that means in terms of you can write Yv is equal to Pv by P or Yv saturated is equal to Ps or Pg divided by P, where P stands for the total pressure. So, we can now here interestingly when you talk relative humidity it is unitless, whereas when talk about humidity ratio it has some unit in the, and these units are expressed in kg of water vapor per kg of dry air. So, that is how it is defined. So, in a sense that although both numerator and denominator are kg, but since you need to separate it out for dry air and the moist air in the humidity ratio, then we have it is assigned a unit. But on the other hand, relative humidity does not have any unit, because it is finally expressed in one unit that is bar, and phi the bar for the numerator and denominator gets cancelled. So, it is a unitless. The another term that is of interest is degree of saturation. So, this is nothing different, but you can mix these two terms relative humidity and humidity ratio, and to define this particular term. So, its two properties when we are linked together, we call this as a degree of saturation, that is mu. It is nothing but the ratio of actual specific humidity to the specific humidity of saturated at mixture temperature is known as degree of saturation. So, mu is equal to omega, which is the actual specific humidity, and omega s, that means if the mixture would have been saturated, then it would have omega s. So, when you put this, we can write their individual expression 0.632 Pv. So, when you talk about omega, we say it is a vapor pressure. When you talk about omega s, this vapor pressure now becomes saturated pressure. So, it is Ps now. So, after simplifying this, we can get a expression mu in the form of Pv by Ps into 1 minus Ps by P divided by 1 by 1 Pv minus 1 minus Pv by P. So, ultimately we have an expression mu and phi that link together in the form of partial pressures of water vapor, saturated air, water vapor of actual state, saturated air, and of course, the total pressure P. And after doing some kind of simplifications, we are able to represent phi as a function of mu and Ps as well as P. So, this is just a corollary of the other two informations. Next property that we are going to talk about is the internal energy and enthalpy. So, thermodynamically when you deal with they deal with different temperatures, the other properties are internal energy and enthalpy, and of course, when we have flowing stream we define in the form of enthalpy. When you have a stagnant stream or control volume system, when you talk about a closed system, then we use the word internal energy. Okay. So, when you talk about internal energy and enthalpy of separate part, we recall this temperature volume diagrams. So, we are looking at a state which is in a TV diagram. At that point, if you want to quantify what is the enthalpy and internal energy, then there are two ways. The total enthalpy can be divided by as enthalpy of dry air plus enthalpy of water vapors. So, this dry air part can be dealt with separately. Ma into Ha, and this Ha is nothing but Cp times T because it is a dry air component, and Mb and Hb is nothing but the vapor pressure component. So, once you know Mv then and Hb you know the mixture temperature, and if it is a saturated is close to value of Sgt, and this value is enthalpy value is close to the saturated vapor state. So, from this we can simplify in terms of per unit mass of dry air. Remember the total enthalpy, if you H divided by Ma. So, if you take Ma separate it out, then with this H by Ma is nothing but specific enthalpy of the mixture. It has two components, one is small ha, that is enthalpy of dry air, and other is omega times Hb, that is enthalpies of moist air. Similarly, we also can have internal energy per unit mass of dry air as two components, internal energy for dry air and internal energy for water vapors, which is nothing but omega times UV, and this is how it is evaluated. And many a times we say, when you say UV, it is nothing but it is a saturated vapor state. So, it is a gas phase, and that is evaluated at mixture temperature, and this mixture temperature is nothing but this particular temperature at which, and that is can be located in the TB diagram. And similar sense we also have entropy. So, entropy has two components as well here, water vapors and dry air, and each components can be dealt with separately. So, in same sense the entropy of the mixture, that is per unit mass of dry air, is S by Ma. It has two component, Sa, that is for dry air, omega times Hb is for water vapor component. So, here the important aspect is that how to find out Sb, entropy of water vapors. Of course, for dry air component we can find out the similar way as you do in the thermodynamic aspects. Now, when you talk about water vapors, so you have to recall our this entropy equations, which is evaluated entropy between two states. So, here the two states are, one is the actual state, other is the saturated vapor at temperature, mixture temperature T and partial pressure PV. So, that is your actual state, but the corresponding reference point to take this difference is the one is if the mixture, if the air is saturated, it would have entropy Sg at temperature T and minus R times ln PV by Pg. So, PV is your vapor pressure and Pg is your pressure when the air is saturated or gas phase pressure. So, this things now becomes Sg times T R ln phi. So, in a way that we can able to express in this form. The next important property is dew point temperature. In fact, this is a very important properties, because we all come across dew in our day to day life, or condensed water vapors. They are part of day to day life, and mostly they happen in the winter, and these water vapors comes as a droplets on the grass during the winter, or sometimes the window panes when you deal with air conditioning systems. Now, what is this dew and why it happens? To understand this particular behavior, we can define this in the thermodynamic sense. First thing is that we take a container in which it consists of a dry air and superheated vapor state. That means, superheated vapor is there, that means thermodynamically we can fix in a temperature volume diagram at state 1. So, in a state 1, as if this is your thermodynamic diagram in which state 1 is defined, and this state 1 is nothing but a volume in which it contains mixture of dry air and superheated vapor. Now, what you do, we want to cool this. Now, if you want to cool this, there are two ways of cooling. Say one is I can go at a constant pressure. One of the method is that in a constant pressure based cooling. So, when I say cooling, so that means from point 1 if I start cooling, when I start cooling a specific volume drops. So, mixture gets compressed, and if you keep doing and you will reach at a state that at one particular point this will reach the saturation curve on this saturation point, that is point D, and we reach the saturation curve, and below this constant below this temperature cannot be reduced further, because if you, that means further system, because we are already crossed the saturation point on this curve, and at same pressure cooling is not possible, because if you do this it is going to change the phase. So, you have to go along the saturation curve. So, to that means at that time your pressure must decrease further. Now, when the pressure decreases also temperature drops, but volume there is a the volume increases. So, in a sense that when you when you reach at a final state 2, that means initially we start with a initial temperature T1 and finally we reach at a final temperature T2, but this is how we talk in terms of temperature. But if you look at actual composition wise, the composition will have in two stages. In one stage we will have at state 2, and that state 2 is nothing but your air and saturated vapor, which is dry air and saturated air vapor mixture at this point 2. Other way will be that we will have some condensed saturated liquid at the bottom. So, this point is denoted in the TV curve as point 3. So, basically 2 to 3 process is a constant temperature process, and this process cooling happens, but here there is a phase change. So, it means that the water vapors change its phase, now they become liquid. So, from where this liquid starts? So, liquid normally starts from the point in which we reach the saturation curve. The first point time when you reach the saturated curve when you are D, when at the point D. So, point D is known as the dew point, and that temperature, if you draw the vertical, then that temperature we can say it is T dpt, dew point temperatures. So, this is the dew point temperature happens that from its initial state, if you do the cooling process at same vapor pressure, it reaches the saturation curve and we reach this dew point temperatures. So, this is how it is explained here, and typically when you deal with pressure values, you have 3 pressures as of now. So, correspondingly initially we have pressure PV1, so this pressure corresponds to state 1, and at same initial temperature, if you draw this vertical, we reach this saturation curve at this point, and at that point your Pg1. Obviously, this Pv1, if you look at this curve, is less than Pg1, and subsequently when you reach at point 2, it will have another pressure, and that is this Pg2, and this Pg2 is also but less than Pv1. So, in this process we are landed with 3 pressures. One is actual vapor pressure which is present in this mixture. Other way is that when at the initial temperature and final temperature, the saturated values of gas phase pressure. So, it is Pg1 for the initial state and Pg2 for the final state. And in terms of mixture wise, we have 2 components. One is air and saturated vapor at state 2, which is saturated gas phase state, and other way is the condensate, which is the saturated liquid state. So, all these things are explained. So, finally, the very basic bottom line is that owing to the condensation, the partial pressure decreases because the amount of vapor pressure present in the final state is less than the initial state. Since the amount of dry air remains unchanged, the mole fraction of water vapor in the moist air increases. So, this is the summary when you talk about dew point temperature. The another approach is that in our psychrometric properties discussion is adiabatic saturation temperatures. So, from this last segment of discussion, we said that if you have initial state, and for that initial state this we have this, if you draw a vertical, so it cuts this temperature T, and this temperature we call this as a mixture temperature, and normally this mixture temperature we call this as a dry bulb temperature. So, we say T, D, B, T. In our last segment we discussed about the dew point temperature. So, in the same pressure PV, if you cool this gas will reach at this point, and if you draw a vertical on this temperature axis, we reach dew point temperature T dPt. So, basically defined two temperature, one is dry bulb temperature, other is the dew point temperature. The another way that we can define this temperature is that we can bring this point to saturation curve. Another approach we can use at adiabatic saturation. So, what does this physically mean? That suppose we have a moist air which is at certain condition pressure P, T and omega, and on this moist air we add water. Now, this moist air whatever state it may be, we keep adding it, so that the final state is the saturated mixture. And in thermodynamically what we say is that entire system is enclosed or given a perfect insulation, so that no heat transfer is possible from this moist air to these surroundings. So, it is a complete adiabatic process. Now, when you say complete adiabatic process, then how do you want to, how you are going to locate that state in this temperature volume curve. So, this particular way we define this, and we go along a dotted line, and this dotted line represents that it is a adiabatic process. Now, when you are adiabatic process, when you deal with and keep adding moisture into this air, so we reach another point, that means we reach at this point. So, this point is nothing but water vapor state in the exit, and that means exit moist air stream is completely saturated. So, that point of time we drop this vertical, we call this as a adiabatic saturation temperature. So, this is how it is defined, and in the psychrometric term, this adiabatic saturation temperature we call this as a wet bulb temperatures. So, it is a TWBT. So, WBT stands for wet bulb temperature. So, very basic fundamental understanding is that for a given state of mixture, there are three temperatures. One is when it is at mixture temperature, that is T dry bulb temperature. Other is we can have a wet bulb temperature. To reach the wet bulb temperature, we have to go through an adiabatic saturation process, and third is we are dew point temperatures, and to reach this dew point temperatures we have to cool this gas till we reach the saturation point, but at constant PV at same pressure. Okay. But so, this is how for a given state three different temperatures are defined. All these things are explained here. There are some thermodynamic relations that can be developed between the humidity ratio and adiabatic saturation temperatures. So, one can think of one can first thing define Pg is the gas pressure, Ts is your adiabatic saturation temperature. So, this point is Pg Ts, and when you reach this point we say it is a we have reached the adiabatic saturation temperatures in this temperature axis, and Hf and Hg is the enthalpy of saturated liquid and saturated vapor. So, a steady flow energy equations can be applied for this model, where Ma times Ha plus Mb times Hb, that is your inlet state, and other inlet is the makeup water that gets added. This makeup water which is getting added, it is m dot b dash minus m dot b, that means final mass minus initial mass of water vapor, and we is equal to final energy, that is in the form of Ma Ha plus m dash b Hb. And remember, when you talk about this makeup water, it is a water state. So, it is water at liquid state. So, that is what it is written as Hw. So, and from this we can find out the humidity ratio. At the inlet state, that is when the air when the moist air enters into the systems, and we also can find out the humidity specific humidity or humidity ratio when the air stream comes out. A simplified expression, this equation can be simplified in this manner, and finally, we land off in this particular expressions. So, this particular expression has information about enthalpy, and this enthalpy needs to be calculated, which is there in their bracket. So, if you want to, here the Ha is to be calculated at this adiabatic saturation temperature. This H has to, that means this arbitrary state, that is this is your arbitrary state, this value is at mixture temperature T. Okay. And similarly, Hg stands for the gas phase. Okay, there is a mistake here, this is Hf and Tas. Okay. So, Hf is your liquid state, and this temperature, this liquid value is to maintain at adiabatic saturation temperatures. Okay. Now, till this point of time we discussed about all the psychrometric properties. Now, we are going to say that how these psychrometric properties can be utilized or discussed in a psychrometric chart. So, a psychrometric chart is nothing but the locating the thermodynamic properties in a chart. So, if you have a particular state which is denoted by this circle, and whereas this psychrometric chart we have this axis of or the shape in this fashion. So, we have a dry bulb temperature axis, we have a specific humidity axis, and for any things for any state within this we require two properties, that means you will be given with the value at two the state at the initial state at two properties value, and when that point we can locate on this chart. Now, on this chart, if you there are lines what we call as these inclined lines, they are nothing but your relative humidity lines, and this particular line is known as saturated line. Now, from this point if you drop a vertical, we reach the dry bulb temperature on the temperature axis, and when you drop a vertical on specific humidity axis, we get the moisture content, and this wherever it cuts this inclined line. So, we call this as a relative humidity value at that point, and from this if you go along same specific humidity line, that means until you reach the saturated point and drop a vertical on the temperature axis. So, this will denote you the dew point temperatures. Another way of thing is that when we go along the adiabatic saturation curve, adiabatic saturation curve is nothing but your constant enthalpy curve. So, if you go along this and reach the saturation point and drop a vertical, so this will give you T W B T wet bulb temperatures, and this particular will be T D B T dry bulb temperature, and at this dew point temperature we say T D P T. So, for a given state there are three temperatures, and there is another line which is goes in this manner, and this line is called as a specific volume line. So, more and all these things is plotted at standard atmospheric pressure, that is 760 mm of Hg, and a more clear picture is shown here. You can see here for in a psychrometric chart how so this value will have same value of wherever you are. So, it will have same value of dBT, WBT and dPT. And the realistic version of a psychrometric chart is going to look like, where I have taken this from the book Moran and Shapiro, Engineering Principles of Engineering Thermodynamics. So, here we can see these charts and it is plotted for standard atmospheric pressure of 1 bar, and for which all the lines with their actual quantification is denoted here. So, basically any processes or change of state of moist air can be located on these psychrometric charts, and their approximate values can be found out. Now, we are going to solve a simple problems which we discussed right now. So, we are given with atmospheric air which has a dBT of 30 degree centigrade and wet bulb temperature of 20 degree centigrade, and we have to calculate the parameters like partial pressure of water vapor, specific humidity, dew point temperature, relative humidity, degree of saturation, density of air in the mixture, density of vapor in the mixture and enthalpy of the mixture. So, first thing is that, as I mentioned, there are two ways in which properties values can be calculated. One way is through the expressions that we defined so far, other way we can use the directly psychrometric charts. So, although there is it is very difficult to remember most of the expressions, but on the other hand, to have a very learner or beginner, it is advisable that you use the formula in the beginning situation to understand the problem, and later on when you have understand the problem, then you can use the psychrometric chart directly. So, in this case, first thing to calculate this property, we also require a term which is called as the expression which we derived for adiabatic saturation. Although it is big expression to remember, but you do not have to remember when you actually deal with the psychrometric chart. So, there is a correction here, this particular term in the denominator will have HFTAS. Okay. Now, this why I have written here, because these things we require in our analysis. So, first thing that we have to say is that why we require in this, because we have to draw this psychrometric chart to locate this state. So, the psychrometric chart looks like we have dBT, we have omega, and we have state which is defined is this point, and the point 2 is nothing but your adiabatic saturation. Now, why I should go here? Because to calculate all these degrees of saturation and enthalpy, we require the corresponding values when the air is saturated. So, because this is the saturated line. Okay. So, the solution that we can start is dBT is given 30 degree centigrade and WBT 24 degree centigrade. Now, first thing we have to find out this omega. So, here you have to use the what you have to use? You have to use the expressions that we know, the CPA. Okay. So, omega we can take as so first thing we have to say this point for point 2 omega 2, and it is at saturation curve. We can write as 0.622, it is PS by P minus PS. So, here you have PS can be calculated, PS is calculated at 24 degree centigrade saturation pressure. This we can calculate using steam table. So, at saturation temperature table of 24 degrees centigrade, we can calculate this Ps, and this value Ps is equal to 0.02985 bar, and then we also have P is equal to 1 bar. So, from this we can calculate omega 2 as 0.0193 1913 bar. Then using this equation we can first thing what we are going to calculate omega 1. So, from this information we are getting back the information of omega 1. So, omega 1 we have two parts, this air part and the water vapor part. So, this we can write 1.005 air, that is 24 minus 30 plus this part. So, for this part we have to recall omega dash is equal to from the steam table at 24 degree centigrade we can find out HFG2 is equal to 2447 kilojoule per kg. HF2 enthalpy value at liquid state 100.7 kilojoule per kg, and again at 30 degree centigrade. Here there are two things, with 24 degree centigrade and 30 degree centigrade we can calculate HW1 as 2556.3 kilojoule per kg. Okay. Now, when you put these expressions here, then we can write omega 1 from this 0.01913 into 2447.7 divided by 2556.3 minus 100.7. So, this will give you omega 1 as 0.0158 kg by kg of dry air. So, once you know the omega 1, then first problem that you can find out is omega 1 is equal to 0.622 Pv divided by P minus Pv. So, here P is 1 bar, Pv need to be calculated, omega 1 is this. So, we can find Pv as 0.025 bar. So, we have specific humidity, we have partial pressures. So, this is B, specific humidity, we have partial pressures. Then we have to find dew point temperatures. So, dPt can be found out. So, at saturation temperature at 0.025 bar. So, this is dPt is equal to 21 degree centigrade. Okay. The next thing is we have to find out relative humidity RH, that is phi, that is nothing but Pw by P saturated. Now, P saturated means at 30 degree centigrade. So, 30 degree centigrade steam table will give you P saturated as 0.04246 bar. So, this we get it from steam table. So, this then we can say phi is equal to, already Pw is known to you, 0.025 divided by 0.04246, that is 58.8%. Then E, degree of saturation. So, degree of saturation, it is mu, you recall our expression Pw into P minus Ps divided by Ps into P minus Pw. So, here P is 1.0132 bar, Ps 0.04246 bar and Pw 0.025 bar. So, this will give you mu will be 0.578. Next is density of air in the mixtures. So, density of air means rho A is equal to Pa by R Ta. So, Ta is your 30 degree centigrades, 303 Kelvin, R is 287, Pa is nothing but P minus Pw. So, Pw is this, so Pa would be 0.98825 bar. So, when you put this here, kilojoule per kg Kelvin, we can find rho A as 1.15 kg per meter cube. This we get mixture. Then density of vapor in the mixtures. So, Pv is equal to omega, we know omega 1 times P rho A. So, omega 1 already you know 0.0158 into 1.15. So, this value is 0.01817 kg vapor by meter cube per dry air. Then last part is enthalpy. Enthalpy H is equal to HA plus omega times HW. So, HA and omega times HW, this is a function of temperature and this is a function of HA plus and omega HB. So, from this we can write this as Cp Ta plus omega times Hg plus Cpw into T dB T minus T dPt. So, when you put this value, all these values there, Cp for air and Cpw for water, Cpw is 1.88 kilojoule per kg Kelvin. So, from this when you put it, we will get enthalpy is 70.8 kilojoule per kg. So, this particular problem gives you entire information for a given state, that is 30 degree centigrades and 24 degree centigrades. So, the next problem that lies here, that for same problem we want to use this psychrometric chart. So, first thing 30 degree centigrades, somewhere here, and 24 degree wet bulb temperatures. So, we go along this and it cuts 24 degree 21, 22, 23, somewhere here 70. So, that point if you draw this, we will have enthalpy 70, close to 70, already we have found out in our analytical expressions. And this particular chord sheet T WBT, and on this line if you go further we can reach T DPT. This is about 21 degree centigrade. DWBT will be about 23 degree centigrades, and from this if you drop a vertical, this is about omega 0.0158 kg by kg dry air, and this point we have RH, this relative humidity is about 58%. So, you can say, and what else, enthalpy of the mixture is approximately 70 kilojoule per kg Kelvin, kg dry air, and of course, we can know this specific volume. So, specific volume at this line 0.09, 0.08, so means a specific volume, or we can say density. So, B will be 0. So, if you look at this 0.9, 0.88, 89, close to 0.88 kg meter cube per kg dry air. So, if you know the specific volume, then you can infer the information about density. So, this particular things is just to demonstrate that how a psychrometric chart is a valuable tool to estimate the thermodynamic properties of moist air. So, with this I conclude this lecture for today. Thank you for your attention.